Have you ever wondered how a multi-million-dollar machine goes from a radical Cold War concept through some absolutely brutal manufacturing processes all the way down to dealing with a tiny 2-millimeter dent on the tarmac? Well, you are in the right place. Today we're diving into this explainer to trace the incredible life cycle of the Su-30 multi-role fighter jet. We're going to explore exactly what it takes to bring a massive, complex machine like this to life, and just as importantly, what it takes to keep it flying. Here's our roadmap for today. 1. Vision of a master designer. 2. Engineering supermaneuverability. 3. Forging the Su-30. 4. A global commercial success. And 5. Real-world maintenance and recovery. Let's get right into it.
Section 1. Vision of a master designer. The radical origins of the Su-27 and Su-30 family.
Picture this, it's the Cold War, and general designer Mikhail Simonov flat out refuses to build a merely good jet. He demands the absolute best. So, when an American F-15 pilot saw Russian test pilot Viktor Pugachev perform the mind-bending Cobra maneuver with Simonov's new design back in 1989, his reaction was literally, "If I meet this bird in battle, I will have to eject." Wow, it wasn't just some neat airshow trick, you know? The fundamental aerodynamic rules of close-range dogfighting had been completely rewritten.
We can trace this evolution pretty clearly. Starting with the first Su-27 prototype in 1977, things really accelerated when Simonov became general designer in 1983. Fast forward to 1993, and the world saw the debut of the Su-30 MK prototype in Paris. It had completely evolved from a trainer into a fully capable, multi-role strike fighter.
Section 2. Engineering supermaneuverability, defying the limits of aerodynamics.
So how did they actually achieve this jaw-dropping agility? The secret sauce is thrust vectoring. Basically, this technology allows the jet to balance in the air and turn in ways that defy traditional aerodynamics. Instead of relying purely on the flow of air over the wings and flaps, these AL-31FP engines have exhaust nozzles that can swivel up to 14 degrees. Think of it like trying to balance a broom on your fingertip. You're constantly adjusting the base to control the top. This literally gives the pilot the ability to point the nose of the aircraft and therefore their weapons almost completely independently of the direction the jet is actually moving.
To put that into perspective, our sources detail this fascinating real-world encounter over the Barents Sea. You had Norwegian F-16s trying to escort a Russian Su-27. Because the Sukhoi design relies on optimal aerodynamic instability and incredibly powerful afterburnerless thrust, it cruised along completely effortlessly. The F-16s, on the other hand, had to constantly engage their fuel-heavy afterburners just to match that exact same cruising speed. That obviously led to rapid fuel depletion, and they were literally forced to break off the escort. It's a perfect example of how raw aerodynamic design translates to actual tactical superiority.
When the jet pulls off one of these extreme angles of attack, it is doing something that shouldn't be possible. For a normal plane, pointing the nose that far off the flight path means an immediate stall on a crash. But for the Su-30 family, it is a perfectly calculated, controlled maneuver. Thanks to that unstable airframe and thrust vectoring, the jet can rapidly bleed off speed and force a pursuing opponent to just fly right past them.
Section 3. Forging the Su-30, the extreme manufacturing process.
Now, designing a supermaneuverable jet on paper is one thing, but actually building a structure that won't rip itself apart under massive G-forces, that is a whole different ballgame. The process starts by heating raw titanium to 950 degrees Celsius and crushing it under a 75,000-ton press. To give you an idea, that is roughly the equivalent of setting a fully loaded cruise ship down on a single component. From there, 5-axis CNC machines sculpt these parts down to micron precision. Finally, massive carbon fiber composite wing structures are cured in giant autoclaves at 6 bar of pressure and 180 degrees Celsius. They literally forge this machine to survive the brutal physical realities of high-G combat.
But of course, a ridiculously strong titanium airframe is basically just a flying paperweight without a serious brain. The jet relies on the BAR's passive phased array radar, which is capable of tracking 15 targets simultaneously and guiding missiles to 4 of them at once. To survive in hostile airspace, it's packed with the Cabini-U electronic warfare system, using active jamming pods on the wingtips to create false targets. And hey, if the absolute worst happens, it's equipped with K-3060M ejection seats, which are widely considered the absolute best in the world for keeping the crew alive.
Section 4. A global commercial success, export dominance, and operational reality.
262. That is a massive number. In the 1990s, the Russian aviation industry was really struggling, but this aircraft essentially saved it.
That 262 represents the active fleet in the Indian Air Force alone. They didn't just buy a handful of jets, they made the Su-30 the absolute backbone of their air defense, cementing it as a huge commercial triumph.
And that dominance really spans the globe. The jet proved incredibly adaptable. We're talking successful customizations for nations ranging from Algeria to Malaysia. China alone operates nearly 100 of these across its Air Force and naval aviation. The fact that this airframe could be adapted to fit Western avionics for some clients and domestic systems for others was an absolute game-changer for its widespread adoption.
But to get the truly comprehensive picture, we have to impartially look at real combat data. In the current conflict in Ukraine, the source material shows a dual reality for the Su-30. On one hand, it's being heavily utilized for long-range tactical strikes and suppressing air defenses. But on the other hand, the data confirms over 15 losses. These aircraft have proven vulnerable to modern mobile air defenses and, quite uniquely, to Ukrainian naval drones equipped with AIM-9 anti-aircraft missiles. It really goes to show that even the most maneuverable jet is operating in a highly lethal, unpredictable modern threat environment.
Section 5. Real-world maintenance and recovery. Grounded by nature. So, you might be wondering what actually happens when a multi-million-dollar jet engine meets a 2-pound bird. Well, all that thrust vectoring and phased array radar means absolutely nothing if you can't keep the jet on the flight line. It turns out, the ultimate enemy of a 30-ton marvel of engineering is a bird strike. They are a massive, constant vulnerability. When these incredibly sensitive AL-31FP engines ingest a bird during a low-altitude maneuver, the consequences for those intricately machined rotor blades are severe.
In a recent Malaysian military case study, engineers found rotor blade damage that had to be marked out with an X. Now, according to the aircraft maintenance manual, a dent exceeding just 2 millimeters or a crack longer than 5 millimeters means the engine absolutely cannot be patched up on the tarmac. It triggers a massive, coordinated effort to completely remove and replace the entire 1,500-kilogram engine. Just think about that. A tiny 2-millimeter dent means replacing the whole shebang. The operational impact of that tiny bird strike is honestly pretty drastic. The data shows that before the repair, the engine's low-pressure air compression efficiency plummeted to 76.4%. That is well below safe operational thresholds, causing low thrust and high fuel consumption. But by strictly adhering to military maintenance protocols, the new engine installation successfully restored that efficiency all the way back up to 92.5%, safely putting the jet back into the fight.
Which leaves us with a pretty provocative final thought. We've explored the sheer genius of its design, its brutal manufacturing, and its gritty maintenance realities. But in an increasingly stealth-dominated, beyond visual range fifth-generation world, what is the future relevance of highly maneuverable fourth-generation fighters like the Su-30? Will supermaneuverability even matter when missiles are fired from hundreds of kilometers away? It's a massive question that aerospace engineers and military planners are wrestling with right now, and one that will undoubtedly define the next era of aerial combat. Thanks so much for joining me on this explainer, and keep asking the big questions.